Hi, this is Jack Jackson again with part 5 of our series of lectures on inferential statistics. This one is on the t-test and the t-interval. T-test and t-interval are perhaps the most used parts of inferential statistics. They're very, very commonly used. Now remember, in all of these tests and confidence intervals, we have some underlying assumptions. What were they for the z-test and the z-interval? Well, remember what we're basically doing. In a z-test, we're testing a sample mean against a known population mean. For a z-interval, we're forming a confidence interval for the mean of a population, and you're doing that from looking at the mean of a sample. Of course, the sample size comes into play there as well. Now, what underlying assumptions do you need for this? Well, the first thing is you need the mean to be approximately normal. So the sample means have to be distributed approximately normally. Now remember, according to the central limit theorem, this is a very good assumption if the distribution of individuals is either nearly normal or if the sample size is large. So if its sample size is bigger than 30, we've usually said that's usually big enough so that pretty much whatever the underlying distribution is, the distribution of sample means is pretty close to normal. We also had another assumption, and that was that the population standard deviation is known. Now this is usually not a good assumption. Think about what we're saying. We're saying we know how variable a population is, but we don't know what its center is. That's not a likely situation. It's not likely that we're going to know well, probably either one, but certainly it's very unlikely we're going to know the population standard deviation. So we have to make an adjustment, and that's exactly what a t-test and a t-interval does. It's basically the same idea as a z-test or z-interval, but we just adjust for not knowing the population standard deviation. So if we look, the basic assumptions for a t-test or t-interval, at least for a one sample t-test or t-interval, are exactly the same as a normal distribution, that is a z-test or z-interval, with one slight change. In the t-test, we're testing for a sample mean against a known population mean and seeing if it's different, if this sample comes from that known population or hypothesized population, the one that comes from the null hypothesis. A t-interval is forming a confidence interval, again, for a mean of a population, just like a z-test and a z-interval. Again, we need the distribution of sample means to be approximately normal. Now, the t-test is often used for small sample sizes, so in that case we need the distribution to be approximately normal for the individuals, or again, we can have a large sample size. So this is a good assumption. But we have a much better assumption here on the standard deviation. We assume that the standard deviation is unknown. That's more likely the case in a real-world situation. So in a real-world situation, really, it's unlikely that you should really use the z-test or z-interval. We go over that first because it's easier to understand and it's easier to explain the concept of a confidence interval and the concept of hypothesis testing in the context of a z-test or z-interval. But a much more realistic situation is the standard deviation is unknown, and in this case we will use a t-test or t-interval. Now, by the way, this assumption of normality for the distribution of sample means is a very important one, but it is satisfied well enough to use the test in any of the following cases. So if the sample size is large, that is, it's over 30, this works no matter what the distribution of individuals is. Remember this from the central limit theorem. Now, for that range of 15 to 30, for those distributions, as long as the distribution is fairly well behaved, that is, if it's unimodal, nearly symmetric, short-tailed, and without outliers, then that still is close enough to normal so that the distribution of sample means is close to normal. For example, remember we even got by with a much smaller distribution when it was, say, a uniform. So we looked at an example and we talked about sampling distributions where we had a uniform distribution and a sample size as small as 5 gave us a distribution of sample means that was quite close to normal. So what are the things that can kind of throw it out of whack and make it to where it's so far from normal that you need that really big sample size? Well, if it's bimodal. Remember, we looked at some examples where there was a bimodal distribution, and those, to sort of get rid of those two humps there, we had to get a fairly large sample size for that to not to show up in the distribution of the sample means. If it was highly unsymmetric, that's another thing that could kind of throw it off. So it's really skewed to one side or the other. Then that really made the situation where it took us a higher sample size. If it's short-tailed and without outliers, that's also good. So if there are outliers, they can kind of throw things off. But if it's fairly well behaved, unimodal, nearly symmetric, fairly short-tailed, without outliers, those are really good situations where a pretty small sample size, maybe sometimes even less than 15, we can get by with. If we want less than 16, that 15 and lower, then we really need the distribution of individuals to be somewhat close to normal. If it's kind of mound-shaped, most of the area, most of that data near the mean, kind of fairly close to symmetric, kind of tails going out to the sides of both sides, especially if they fade away pretty quickly, no outliers. If it's got all of that, then we can get by with an even smaller sample size. But if we have a very small sample size and it's from a highly non-normal distribution of individuals, then we've got to use something else besides a t-test. You can't always use a t-test. You have to establish this normality requirement in one of these ways. And in these other cases, there's a different type of test that you'll have to use. It's usually some sort of what's called non-parametric methods, and we probably are not going to get a chance to go over those in this particular class, but your book does talk about some of them, or you can look up a more advanced statistics book to see what you do in those cases if you're forced into that sort of a situation. In a real-world situation, probably your best bet, if you're in a highly non-normal distribution, just bump up your sample size. Get it up to above 30, and then you're in good shape. Even though it may cost more money to do that sample of that size, it's probably worth it in that case. Now, remember that what we have here when we're talking about a z-test or a z-interval, what we do is we start with our distribution of x bars, which is normal, or approximately normal, and what we often do to actually compute the z statistic is we usually standardize it. Okay, and of course that means find a z-score. That's why it's called a z-test or z-intervals for a z-score. And a z-score, if you remember, is we take our thing that we have, our sample statistic, our x bar, we subtract the hypothesized mean, mu, and divide by the standard deviation of that sampling distribution. That is the standard deviation of the x bars. Of course, the standard deviation of the x bars is the standard deviation of the x's divided by the square root of the sample size. And so this formula, x bar minus mu over sigma of the x's divided by square root of n, that, when you do that and find that z-score, remember they're going to be distributed normally with a standard normal, that is a normal with mean 0 and standard deviation 1. All we really do in a t-test and a t-interval is we replace the sigma of the x's by s. And what is s? S is the standard deviation of our sample, the sample standard deviation of our sample. Of course, that's the s with the formula n minus 1 in the denominator. So just do use your calculator or Excel or some statistical software to compute that sample standard deviation, and of course your sample x bar, and we can test this against a hypothesized mu in a t-test by finding this statistic. So this statistic, x bar minus mu over s divided by square root of n, we're going to call that t, and t is actually distributed by a t distribution. Okay, and it depends on the sample size n. So there's actually not just one t distribution. There's a t distribution for every possible sample size. And the one less than the sample size is called the degrees of freedom. Okay, so n minus 1 is the degrees of freedom, and we have a t distribution for every possible degree of freedom. Now, these t distributions are actually called students' t distribution. It's actually a family of distributions that are similar to the standard normal distribution. N minus 1 is called the degrees of freedom, and there's one of these distributions for each degree of freedom, so there's a whole family of these things. They're all bell-shaped. They all have a mean 0. They all have standard deviations that are greater than 1, but they approach 1 as n increases. So as n gets bigger and bigger and bigger, each of the standard deviations is going to get smaller and smaller and smaller, closer and closer and closer to 1. So the larger n gets, the closer the graph is going to get to the graph of a standard normal. We'll look at some actual pictures here in just a second. Now, the bad news is the formula for this is rather complicated, actually much more complicated than even the normal formula, which is fairly complicated. So the formula for the TPDF is fairly complicated. I'm not even going to show it to you this semester. That's the bad news. The good news is that the TPDF, the TCDF, and the inverse T commands are all available on the TI-84, and they work just like the ZPDF, that is the normal PDF, the normal CDF, and the inverse normal functions. Just like you use those for the standard normal or Z distribution, we're going to use the TPDF, TCDF, and inverse T for the T distributions. The only difference is we have to input the degrees of freedom into them as well. And so that's the only real difference. Now let me talk a little bit about this word students distribution, students T distribution. It really should probably be called Gosset's distribution because he's the one that developed this. His name was W.S. Gosset, but he published under the pseudonym Student. And let me explain why he did that a little bit. He was a student at Oxford, and then he started working for the Guinness Brewing Company. And he had lots of data on the brewing process. And he went back to school a little bit and studied with a guy named Pearson, who was one of the founders of many aspects of statistics and probability. And then went back to the Guinness Company again. And when he was at the Guinness Company, he did a lot of work with this data that they had to help out their brewing process. Now, he wanted to publish, but Guinness wouldn't let him publish under his own name. They said, okay, you can publish, but you have to use a pseudonym, and number 2, you can't use any of our actual data from our brewing plant, our brewery. So, of course, that's exactly what he did, and the pseudonym he chose was the name Student. So this is forevermore known as Student's T distribution. One of our authors of a textbook we used recently, a guy named Triola, had an interesting story. He said he would go to no lengths, he would go to any length it needed to make sure that he understood statistics and that he could relate that to his students. So he felt it was his duty to visit the Guinness plant, and he actually went over to the brewery there. And of course, while he was there, of course, he looked at some of their the historical stuff there, but then of course he also had to make sure he sampled a lot of their product, and he felt that was his duty as a teacher. So I haven't done that myself yet, but who knows, maybe someday. Students T distribution. Now let's look at some pictures of it. Here is the graph of PDF for students T distribution for 1, 2, 3, and 4 degrees of freedom. That is for a sample size of 2, 3, 4, and 5. Let's start with 1 degree of freedom. A sample size of 2 gives you the dark black curve. Okay, then 2 degrees of freedom is the red dashed one, the green one is 3 degrees of freedom, and the blue one is the 4 degrees of freedom. Notice that they're all very similar to a normal curve. They're a bell-shaped curve. They're all centered up on 0. Pretty much looks kind of like a normal curve when you just look at it. Kind of hard to tell it apart just by looking at it. But it's a little bit different than a normal curve, but very, very similar. Notice that as we increased the degrees of freedom, we decreased the variance, and we decreased the standard deviation. So the mode there in the middle at 0, which is the mean, median, and the mode in all the cases, got higher as the degrees of freedom got higher, and the tails got sort of smaller, and it sort of pulled in towards the mean a little bit as we let the degrees of freedom go up. Here's another one where we have 5, 10, 15, 20, and 25 degrees of freedom, and especially by the time we get to 25 there at the top, it's starting to look quite a bit like a normal curve. Let's compare it to a normal curve. This goes back to 5 degrees of freedom. That's the red dotted curve, and the black one this time is the standard normal curve. So you can see that the t-distribution is a little bit more variable. The tails are a little fatter. The mode is not quite as high in the middle. There's a little less area right around the mean. But, basically the same kind of a shape, very similar. I'd still call this a bell curve, very similar to a bell. But it is a little different than the normal curve, a little more variable. However, notice what we've got here. So watch here. This is degrees 15, degrees of freedom, and the other one's 5. Go back to 5. Look at it. And the black curve is not going to change as we go from back and forth here. The black curve is the standard normal. But as we go from 5 degrees of freedom to 15 degrees of freedom, notice that we're much more like the normal. In fact, the bigger the degrees of freedom get, the closer it gets to standard normal. So here are sort of side-by-side graphs with both the normal and a t-distribution, and this upper left is 5 degrees of freedom, upper right is 10, then we got 15, and the lower left is the 20 degrees of freedom, and of course you see the 20 degrees of freedom is getting quite close to a normal curve. Here's one with 31 degrees of freedom. That's a sample size of 32. Notice this one is extremely close to a normal curve. Still not exactly the same, but very, very close. Because this is so close, many people will actually use a standard normal instead of a t-distribution if the sample size gets large, if it's above 30, or especially if it's really big, like above 50 or something. So, for many authors, when you look at elementary textbooks on statistics, they will talk about a large sample size method versus a small sample size method. And they'll say if the sample size is greater than 30, that there's not very much difference in the t-distribution and the standard normal distribution, so they'll prefer to use the z-test and the z-interval if the sample size is greater than 30, even if they don't know sigma. And what they'll do in that case is just use S in place of sigma. We will not take that route in this class. In this class, we will always use the t-test and the t-interval for inferences about the means if the standard deviation of the population is unknown, regardless of the sample size. This is actually more accurate. Okay, it'll give us a more accurate confidence interval, a more accurate test, and it's actually easy to remember because you've just got a very one-step simple determination. If we know sigma, not likely, then we're going to use a z-test or z-interval. If we don't know sigma, that is the population standard deviation, then we're going to use a t-test or a t-interval. So most of the time we're going to end up using a t-test or a t-interval in a real-world setting. Now, there's an applet that I found online. Here's the URL there that you can click on, the hyperlink. And this one shows both the t-distribution and the standard normal distribution for both the PDF on the left and the CDF on the right. You can do this and change the t-distribution. The normal distribution stays the same, but we can change the t-distribution by this slider. Right now it's set at 8 degrees of freedom, controlled by this slider. And it also tells us some parameters and things. For example, the mean is 0, and that's not going to change. The mean's always 0. The variance is going to be bigger than 1 for the t-distribution. The standard normal, the variance is 1. And as we let this get bigger by sliding the bar to the right, this variance is going to get smaller and closer to 1. The skewness is 0 because it's perfectly symmetric about the mean, which is also 0. Kurtosis we haven't even talked about in this class, and the interquartile range we've got there as well, so we can figure that out. And you can see how that will change in a minute. And over here on the right, these numbers at the bottom are actually the deciles or percentiles. They're actually the deciles, but this is percentile, the 10th percentile, the 20th percentile, the 30th percentile, or the first decile, second decile, third decile. And you can also see the CDF over here, and of course, no surprise, it looks very much like the CDF of a normal distribution. Let's see if I can actually pull this applet up and take a look at it. Alright, so here's the applet, and right now I have it at 1 degree of freedom. So the green curve, if you can see that here on the left, is the normal curve. That's the normal CDF, and the normal, PDF on the left, and CDF on the right. So probability density function, or density plot they call it, on the left. The distribution plot is what we're calling the cumulative distribution, or cumulative density function. That's going to be on the right. The CDF on the right, PDF on the left. And the blue is our t-distribution. And we have just 1 degree of freedom. So it's a sample size of 1. Let's look at 2, 3, 4, 5, 6. If you notice, as we go out, that variance is getting smaller. And the interquartile range is coming in as well. And so, you see as we move this to the right, we're getting closer and closer to the normal. Start over. You can see it in motion. Look at the PDF on the left. It's getting closer and closer to the normal. Now let's look at the CDF on the right. It's also getting closer and closer and closer as we move this to the right. We ended up with a sample size of 50. If it's that big, there's very, very little difference in these. Okay, and so this allows you to do, I think allows you to print this out, to save it as a JPEG instrument, or actually a couple other formats there. And so this will give you an opportunity to experiment with this. So I encourage you to try this out yourself. Okay, so let's continue our slideshow here. So, t-tests and t-intervals. We can solve problems involving inferences about means when the sample size is unknown. We use the t-test for hypothesis testing and the t-interval for confidence intervals for the mean. The interpretation and execution of these problems is exactly the same as we would do with the standard normal, z-test, and z-interval. The only difference is we make a couple of quick little substitutions. In the calculator, we're going to use S in place of sigma. We'll use the t-PDF in place of the normal PDF. Now, the standard normal PDF, we only have to input an x. We can leave off the 0, 1 if we want. And that's just the standard normal PDF. For the t-PDF, we have to put the x, but we also have to put our n-1, which is our degrees of freedom. Just as we use a normal CDF to find areas under the normal curve from a left input to a right endpoint, that's how we put a normal CDF. Well, we can do the same thing for a t-CDF, give it a left and right, but then we also give it degrees of freedom. We use the t-PDF to graph. We use the t-CDF to graph, well, the t-PDF will graph the bell curves, and the normal PDF as well. The t-CDF or normal CDF will graph the CDFs, or compute areas, compute probabilities. The t-test is used in place of the z-test for a hypothesis testing, and the t-interval is used in place of the z-interval. And these are all found on the calculator, and you input the information just like you would on a z-test or z-interval, except we used the t instead. So let's see if you can do this. Use your graphing calculator to graph the t-distribution for a sample size of 10. See if you can go ahead and do this now. Find it on your calculator and plug this in your calculator and graph it. Press pause now. Okay. Well, notice first of all that the degrees of freedom, which is n minus 1, sample size minus 1, will be 9. And of course all we have to do is t-PDF of x comma 9 in our graphing window, our y equals. Now, so you have y equals, push that, and then you want to type in t-PDF of x comma 9. Now to get t-PDF, you get it the same place you get z-PDF. You go to distributions, which is second variables, second VARS for distribution, and you'll see it down there pretty soon. I forgot which number it is, but plug that in. Then we need to figure some appropriate window. I'm going from -5 to 5 here for the x's, and -0.1 to 0.5 for the y's, and that actually works out pretty nicely, and we see something that looks kind of like a normal curve, but it's actually a t-distribution. So there we go to graph it. Now, so let's graph the CDF for our distribution now. And in this one, it may be useful to plug in something for -infinity. Let's use -50 in this case. That works out pretty well. So graph the t CDF now. Press pause. Come back when you've done it. Well, here's what we have for the CDF. Again, it's t CDF. You go from left to right. Left is going to be -infinity, which is, we're going to use -54, x, and then we have to give it the degrees of freedom, which is 9. And I use about the same window, except I need the top to go up to about 1. I went to 1.1. And so we graph it, and we get that basic shape that we should be familiar with now, that we get in many, many of the CDFs. Now this graphs are kind of slow, because of all the approximation techniques it's using to get this to work out. But it does come out and graph a nice thing. Of course, you can do an inverse t or a cumulative t by doing a trace, or for a probability that t is less than a certain number. And to find the inverse probability, you could draw a horizontal line and do a calc intersect. But we also have an inverse t built in the calculator, so we really don't need to do it that way. Okay, now let's put this to work for us in an example. Suppose we have a machine that fills cups with coffee, and a sample of size 20 is taken, and we find that the average amount filled in this sample of 20 is 8.05 fluid ounces. And the standard deviation, the sample standard deviation of that sample, is 0.1 fluid ounces. And let's also say that we plot our data on a dot plot, and it looks sort of kind of like normal, at least fairly close, kind of humped up in the middle, tails off to the side. Doesn't have any real dangerous things like a lot of outliers, doesn't have any outliers, or it's not highly unsymmetric or anything like that. So it's close enough to normal that a sample size of 20 would suggest that, okay, this is going to be a normal distribution for the x bars. So describe the distribution of sample means. Well, I kind of already gave away. It's the individuals are nearly normal in distribution, so the sample means are approximately normally distributed. And it's a sample size of 20. That's not above 30, but it's still a pretty big sample size if your original stuff is fairly close to normal. So we know that the distribution of sample means is pretty much normal. It's close to normal, and it's going to have the same mean as the distribution of individuals, but it's going to have a smaller standard deviation. The standard deviation of individuals divided by square root of sample size is going to be the standard deviation of our x bars. So this is the setup we need for a t-distribution of if we're going to try to do any hypothesis testing or confidence intervals. So the t statistic, that is, if you take x bar, and we do this over and over and over again with a sample of size 20, and we do x bar minus the true mean of the distribution, divide by s over the square root of n, that's going to be approximately a t-distribution with n minus 1 degrees of freedom. Now let's suppose this machine is supposed to distribute 8 fluid ounces of coffee. So our null hypothesis will be that this machine is distributing 8 fluid ounces of coffee. That's the mu. That's the mu sub 0 or mu, our hypothesized mean. So the test statistic that we're going to find, a t, is going to be our x bar minus 8 divided by s, 0.1, divided by square root of n, that's square root of 20. So x bar minus 8 over 0.1 divided by square root of 20 is going to be a t variable. It's going to be distributed with a t distribution with 19 degrees of freedom. Remember, 19 is sample size minus 1, 20 minus 1 for 19 degrees of freedom. So if this really did have a mean of 8 fluid ounces, this would be it's sort of a standardized version of our distribution of sample means. Now, we take a sample size of 20, and let's find a 90% confidence interval. Well, we can compute this directly with our calculator, just like we do a z-interval. So we go to stat, and we go left arrow so that we're on tests, or right arrow twice. And then we go down to number 8, and we see that that's a t-interval. It's actually just one below what you can see on the front screen. But if you know it's 8, you can just press 8, or you can arrow down to 8 and hit enter. And this second screen comes up. You want to make sure you're on stats in this case. And we enter our x bar, which is 8.05. We enter our standard deviation of our data from our sample, which is 0.1. And we enter our sample size, which is 20. And we tell it what confidence level we want. In this case, we're wanting a 90% confidence interval, so we put 90. We leave off the percent sign, just 90. Not 0.9, but 90. And then we go down here and highlight the calculate and hit enter, and it produces our t-interval there. It also tells us our x bar, our s, and our n, which in this case we actually entered those. And of course then our confidence interval, our 90% confidence interval for the true mean is 8.0113 and 8.0887. Notice, by the way, that the hypothesized mean of 8 is not in that 90% confidence interval. So right there, that tells us that we're probably in a situation where it's actually filling the cups a little bit more than what they've said they're going to. I don't have an example of one of these in this particular lecture, but if we had a set of data, we could put that in our list, just like we do for z-test. You can go to your list by going to Stat, Edit, say put in L1, all of your data, come back and then hit Data here instead of Stats, and it will say, it will compute X bar and S from the sample. It will even compute N from the sample. The only thing you have to give it at that point is the confidence level. And then when you hit Calculate, it will calculate the t-interval from that, and it will output the X bar, the S, and the N. So if you actually had the 20 cups of coffee, we actually had their volumes for each one, we could actually type that in a list, and then it would run everything for us from there. Alright, now the machine again is supposed to distribute 8 fluid ounces of coffee. What's the probability that the average of a sample of 20 cups from this hypothesized population is more than 8.05 fluid ounces? We want to compute and illustrate this here. See if you can figure this out. Remember, hint, you're going to have to use a t-distribution here because we don't know the sample size of the... We do know the sample size. We don't know the standard deviation of the population. Use a t-distribution. Press pause now. Well, here we are back again, and so I can do this by, I can actually shade it in, and this will compute everything for me. I can go to distributions, which is second, VARS, second variables, and then right arrow to draw, and choose number 2, which is a shade of t. We have to put in the t statistic. Well, in our case, that's the 8.05 minus the hypothesized mean of 8 divided by the standard deviation of the x bars, which is 0.1, which is our sample S, sample standard deviation S, divided by square root of sample size. So you can see all that plugged in. Then comma, 50 and 19. So what is the 50? The 50 says we're going to go up to 50. From 50 on. Okay, so we're going from our x, that's our left, to our right bounds. So the left bound is our actual t statistic that we figured out. Okay, and the right is, well, it should be infinity. I'll just use 50 in place of infinity here. And then the 19, what's that? Well, that's our degrees of freedom. And so when you do this, it will finish it up and shade it. And the area is fairly small, so it's kind of hard to see it, but it's actually shaded here to the right. And it tells us the area, which is our probability that we're looking for, 0.01877. It tells us a low end of 2.23607. What is that? Well, that's the t-value for our sample mean. So that's our sample. So if you take the 8.05 minus 8, divide by 0.1 over the square root of 20, that's where you're going to get the 2.23607. That's our t statistic. And we're going from there to, well, it should be to infinity, but we use 50 as our estimate of infinity there. And then we use 19 for our degrees of freedom. You can also, let's actually look at this. Let me actually show you this. Let me actually show you this on the calculator. So we can go to second variables, distribution, right arrow, draw. We want to choose number 2. And we're going to shade our t. Actually, before we do that, let's actually do it this way. Let's figure out our t statistic. So it's 8.05 minus 8. And we're dividing by, parentheses, 0.1 divided by the square root of 20. And that's going to be our t statistic. That's our 0.23607. It rounded off here. Now we've got a better value for it, 2.236067977. A few more decimal places there. And so now we can go back and draw it out now. So we can go to second variables, gives our distribution, either left or right arrow to draw. We want to choose number 2. And our left endpoint is our what we just figured out, our previous answer. Our right endpoint should be infinity. There's no endpoint, but we'll put 50 there for close to infinity. And that works pretty well for the t distribution. 50 for infinity, negative 50 for minus infinity, pretty much no matter how many degrees of freedom. But we do have to put in the degrees of freedom, which is 20 minus 1, so that's 19. Close that. And if I enter, this will go ahead and shade it for us. Here you can actually see it a little bit. It shades that for us. Okay, and you can see it shaded a bit there in the right. And this one has a little bit different Y scale than the last one, so we actually can actually see a little bit of it graphed. But again, we see this worked out. Okay, quit. Now, what I want to do next is I could actually figure that out without actually shading it also. I can go to second distribution and do a normal CDF, and again I can use my, well, 2.236067977, and we want to go from there to infinity. We'll use 50 again, and the degrees of freedom is 19, and this should compute the same area. It says that area is 1. Oh, that was a normal CDF. Excuse me, this should be in a T-CDF. Let's try that again. T-CDF. Let's try again. Okay, T-CDF. There we go, number 6. T-CDF. T-CDF, left endpoint was about 2.23607. We'll just round it off to there. And then we want to go out to infinity, 50 and 19 degrees of freedom. There we go. This should give us our area. This should be the 0.01877, and we have some more digits there, but that's the same as what we had over here when we did it in the draw screen. So you can actually compute it, probabilities there, or shade them, just like you can with the standard normal distribution. Okay, let's go back to our slideshow now. Alright, so this time we're again looking at our machine, filling up our cups of coffee. Same information as before. Nothing's changed. Let's look at a sort of a classical method of figuring out a hypothesis test for this t-distribution. Let's find the critical value associated with the right-tailed test for alpha equals 0.05 and also the test statistic associated with this sample. See if you can figure that out now. Press pause and come back when you're done. Well, we already computed the test statistic. Here it is. It's 8.05 minus 8 divided by 0.1 divided by square root of 20. That is x bar minus mu, the hypothesized mu, divided by s over the square root of the sample size, square root of n. And that's our 2.236067977 as far as our calculator will go. Now the critical value is an inverse t. Remember, the critical values we found on a standard normal by an inverse normal. We're going to use an inverse t. And just like an inverse normal, the first number that you put in on the inverse t is the area to the left. So if it's an alpha of 0.05, that means we have, and it's a right-tailed test, that means there's a 0.05 to the right. Nothing, that's all, the tail is on the right. So that means there's 95%, or 0.95, is the area under the curve to the left, or the probability that it's less than this particular t-value is going to be 0.95. This is the 95th percentile, in other words. So you just do inverse t, 0.95, comma 19, and we get that. Well, let's look at our calculator. We can actually pull that up again. So on our calculator, that's going to be second distribution. We need an inverse t, which is number 4, and we plug in 0.95 and put in our degrees of freedom, 19, and that'll give us our t-value, which is our critical value, critical t-value. Now, how do we make the decision? Since this is a right-tailed test, if our test statistic is bigger than this critical value, then our test statistic falls in the rejection region, in the critical region that we reject. And so this is a reject case. In other words, there is enough evidence to show that this is filling up more than the hypothesized 8 fluid ounces. So with this particular alpha level, we do have enough information to reject the hypothesized mean of 8 ounces in favor of something larger than that. So we have shown that we prove beyond a reasonable doubt that the true mean is larger. Now to actually do this test, I usually wouldn't do it this way. I just wanted to show you how the inverse t worked and so forth, and also remind you a little bit about how hypothesis testing works. But I would actually just use the shortcut that's built in the calculator. So see if you can use the shortcut of a t test in the calculator. See if you can figure out how to do it on your own and then come back and test it out. Try it yourself for now. Press pause. So here we go. The t value is x bar minus 8 over 0.1 over the square root of 20, and that's our test statistic, which is approximately distributed as a t distribution with 19 degrees of freedom. And so when we do this on our calculator, we're going to go to stat, test, it's number 2, t-test. And in this case we have summary statistics, so we're going to go to stats. Notice our null hypothesis is that the mean is 8, the true mean is 8. That's our status quo assumed mean, because that's what they have. And what we want to do is prove that it's different than that. We want to prove that it's greater than 8. So we have to assume the opposite. We assume that it actually is 8, and then we have a one-tailed test for our alternative hypothesis is that mu is greater than 8. Our summary statistics are, for our sample, the sample mean, x bar is 8.05, the sample standard deviation, s is 0.1, the sample size is 20. So when we go to t-test, we've got this screen here, we put it on stats, Mu sub 0 is our hypothesized mean, which is 8. Our x bar is, our sample mean, 8.05. S sub x is our standard deviation of our sample, actually, which is 0.1 of the individuals in our sample. So it's S sub x, and it's 0.1. And the sample size n is 20. And then we have to choose which one of these three things, not equal to 0, less than, or greater than mu naught, for mu, that should describe our alternative hypothesis. Notice our alternative hypothesis is that mu is greater than mu 0. Mu sub 0 is 8, remember. So mu greater than mu sub 0 is our right-tailed test, and so we select that one. If we select calculate, we get this screen that says t-test with the numbers and things on it. If we select draw, we get this bottom right screen. So if we select draw, it actually shades out this. This is really the same thing that we just drew. Well, no, it's not either way. This is actually the drawing for the p-value. The last drawing that we did, where is it? This drawing, well, you can't see it as well here because it's zoomed in too much, but we could see it a while ago when I actually had the calculator up. That area was an area of, let's see, more than 8.05 ounces. Yes, that area still was the same as this one that we have over here. That is the p-value. So what we had there was the actual p-value. We could actually graph the alpha value by graphing this out. First figuring out an inverse t for alpha, which we just did here, 1.72. Let's actually do that. Let me show you that with a calculator. So if I want to graph the alpha region, here we go. So first of all, we need to compute the critical point that goes with it, which is this right here, 1.79. Let me store that as something so I don't have to type this stuff again. So I'm going to store that as, how about C for critical value. So there's my critical value. Now let's actually draw this in. So we want to do this, but draw it for that value. So I'm going to clear my drawing out, which is going to clear it out completely. And then I'm going to go in and go to distribution, right arrow, I'm going to shade a T, and I'm going to shade it from that critical value, which was alpha C, or I could just said previous answer here, comma, and go to infinity, so we'll just say 50, and then the degrees of freedom again, which is 19. And this should shade it for this. So what this is going to shade is the alpha value. So this area here is the alpha, and this boundary of this is the t value of 1.72913. So that alpha value there is 0.05. You can see that shaded. Now if we want to shade in the value of the p-value, a couple of different ways we can do it. One is the way we did it before, which is again go to, let's clear our drawing out first, and then from here go to distribution, draw, shade a T, and we go from our test statistic, which I've got it written down over here so I don't have to figure it out again, 2.236067977, and we go from there up to infinity, well 50, and degrees of freedom 19, and this is going to shade it out. This time what's shaded is the P area, the P value, okay, which by the way we notice is smaller than the alpha value. Okay, go back to our slideshow here. And so we have this worked out. Let me actually do it the way I would normally do it. Let's go ahead and look at this too. Let's go back to the calculator. Back to the calculator, clear the drawing. And what I would do if I were going to do the t-test, I would actually go here and let's see, this is under stat. So from the home screen, we just go to stat. I'll left arrow to test, and it's number 2, the t-test. go by data, put in 8 for mu naught, 8.05, 0.1, everything's in here from last time. So if I go to here and go, let's say I go to draw now, it's going to draw exactly the same picture that we just had. So notice when you do draw on one of these tests, whether it's a t-test or z-test, the area that's actually shaded in your drawing is your p-value. And so the boundary of this region is our test statistic 2.2361, and the area is the 0.0188, which is our p-value. You can also find the p-value without having it draw it by doing the same thing. No, I keep going the wrong way. Statistics, test, and go to t-test again. Everything's still in there from before, but this time just go to calculate and hit enter, and it gives you the what we're testing. That gives you the alternative hypothesis is what's up there. Mu is greater than 8. It gives you the t statistic 2.236067977. Sometimes it's called t star or t asterisk. The p value is there, the x bar value, the s of x, and the n. Of course, in this case, those last three numbers we actually typed in, as well as the 8 at the beginning. Now, of course, here we have a p-value. So we're using a p-value here, and we're comparing it to a given alpha value of 0.05. And so this, remember, we reject the null hypothesis when the p is less than alpha. So this is 0.1877. That's less than 0.05. So we reject the null hypothesis in favor of the alternative. And so we say that there is compelling evidence to suggest that this mean is actually, the mean of the sample is actually larger than the hypothesized mean of 8. So what's happening is this particular machine is actually filling the cups more than the stated 8 ounces. We have overwhelming evidence beyond a reasonable doubt that this is actually happening. Now, that's at the alpha equals 0.05 level. If we had a higher level of alpha, say 0.01, okay, then we would not have met that threshold. So notice once again, as with the z-test, whether you reject or not depends on the alpha level that you pick. The nice thing about the p-value approach is that if you report that p-value, if somebody doesn't like your choice of alpha, they don't have to redo the whole test without any kind of calculator or anything. They can just look at that p-value, compare it to whatever alpha they feel comfortable with using. So this gives us a t-test and a t-interval. Let's review real quickly that it is used when we do not know the mean. We're trying to find the mean of a population, or we're trying to, and so we use a t-interval to approximate that. Or we're trying to compare the mean of a sample to a hypothesized mean of a population and try to see if there's a difference or not. Gives us a way to quantify this and to see if any difference is from just normal, regular variability within that hypothesized distribution, or if this comes from a completely new distribution, if something's really different. Finally, these are used, unlike the z-distribution, a t-distribution is used when you have when you do not have a standard deviation of the population known. So again, this is a much more likely used test. This is one of the most used tests in statistics.